In this video, we will learn about circuits and the magnetic fields they create. Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across 2 points. In other words, the current I is equal to voltage over resistance. Current is generally measured in amps, denoted by capital A. Voltage is measured in volts, denoted by capital V. And resistance is measured in ohms, denoted by a half circle symbol. It's important to understand the relationships between these variables. As current increases, voltage increases. As current decreases, resistance increases. It's important to know these relationships. So here, resistance would be decreasing, voltage would be decreasing. It's important to know these relationships to be able to understand how exactly Ohm's law works. So usually when we see a circuit, it's drawn out a little something like this. This is a very simplified version of a circuit. Here, these two lines are representing the battery. The longer line denotes the positive side of the battery. The shorter line is the negative side of the battery. It's important to know that whenever the current is flowing through a circuit, it will flow from the positive side to the negative side. So in this specific current, in this specific circuit, the current is flowing around this way, will flow around this way, and back up to the battery. Little spikes that you see in a circuit are the resistors. Resistors work to slow down the current or take away from the currents. Now, what exactly is the current? The current is made up of a bunch of tiny charged particles moving in the same pathway, and their movement is pushed forward by the volts that the battery supplies. So a great analogy to compare this to help you understand is a roller coaster. So when we think of a roller coaster, we have a track, which we can make analogous to the wire. We have little people that are riding on the current or on the track, which we will call the current. So we will make the current analogous to the people on the roller coaster. And as I mentioned earlier, the volt from the battery is what pushes that current through the wire. So in this case of the roller coaster, that would be the cart carrying the current, cart carrying the people. And if you've ever been on a roller coaster, you know that once you get to the bottom of a big hill, a big drop, or around a loop, the roller coaster tends to brake and slow down. So we will call these mini brakes or slowing of the people on their cart the resistor. We'll make that analogous to the resistor. So if person 1 is standing right here and person 2 is standing over here, when this roller coaster drops down this big hill and up, person 1 will be able to feel the gust of wind that the cart creates, right? Person 2, however, will not feel the gust of wind because they're too far away. So in other words, if you want to feel the gust of wind from the roller coaster, you need to be within a certain vicinity. You need to be close enough so that the cart can have an effect on you, its wind. This is analogous to a magnetic field. A magnetic field is a region around a magnetic material or a moving electric charge within which the force of magnetism acts. In other terms, the area that the proximity you have to be in to feel the gust of wind from the roller coaster or the magnetism from the current traveling through the wire. Magnetic field is measured in Teslas, denoted by capital T, and oftentimes in problems we'll see it called the B field. So the B field and magnetic field are interchangeable. When we are denoting the B field, as I said, it's an area, but when you denote it on paper, you use either X's or O's. When you use an X, it's that the B field is going into the paper. In other words, the area is behind the paper. Or use O's for the B field to be out of the paper. In other words, in front of the paper. So a way to keep track of how the current and the B field relate to each other is your right-hand rule. Your thumb should always be pointed in the direction of the current, the tips of your finger in the direction of the B field, and the palm of your hand in the direction of the overall force of the field, right? So in the example of the circuit that we have drawn over here, if we were to look at just the left side of the circuit, the current would be traveling upwards in this instance, up. So if you point, let's say that the B field is going into the page, right? So your fingertips should be pointing at your screen, and your thumb should be pointed upwards because it's the direction of the current. Therefore, your palm should be facing left. So on this left-hand side, the force is going to your left. Now, if you rotate your hand as the current travels, so the current's going up, it turns right, begins to travel right. So you then rotate your hand so that your fingertips are pointing at the screen. Your thumb is pointed to your right, so therefore the force would be up at the top. We continue this process to the right and to the bottom. Now, as you can see, we have a top force, a bottom force, left and right. Therefore, there is no overall net force. All of these forces cancel out. When we combine the idea of Ohm's law and the idea of a magnetic field, we get Lorentz law. Lorentz law is the combination of electric, Ohm's law, and magnetic force, the B field, on a point charge due to the electromagnetic fields. When we combine these, we get that Ohm's law is equal to the force is equal to the current times the length of the wire times the magnitude of the B field, how much wind, times the angle between the B field and the wire. So earlier we suggested that the B field was going back into the page. As I mentioned, you're drawing the front plane of the B field. So this is from the front. However, if we were to look at things from the top, we would see the B field going back, right? Because if this line right here is the page that you're looking at, it's going back into the page. The circuit from earlier would intersect the plane perpendicularly. If we were to see the top, we would only see the top of the circuit. So when these two intersect, they create a 90-degree angle. So we would call this one the sine of 90. Now, of course, there are instances where the angle is not a perfect 90-degree angle, and in that case, you would calculate the angle. But for this purpose, we will keep it at a sine of 90. Okay. Now let's try to apply those three ideas to one problem. So the problem says, a device called a railgun uses the magnetic force on currents to launch projectiles at very high speeds. An idealized model of a railgun is illustrated in the figure above. A 1.2 volt power supply is connected to two conducting rails. A segment of copper wire in a region of uniform magnetic field slides freely on the rails. The wire has a 0.85 milliohm resistance and a mass of 5 grams. Ignore resistance on the rails. Okay, so question A wants us to find the current. So if we remember from the beginning of the video, Ohm's law states that current is equal to voltage over resistance. We are given the voltage of 1.2 volts, and the resistance is given as 0.85 milliohms. To go from milliohms to ohms, we multiply times 10 to the negative 3. And we plug these values into our equation. So we'll do 1.2 volts divided by 0.85 times 10 to the negative 3. This gives us a total of 1,411 amps. However, if you look at the values given in the problem, we're only given up to 2 significant figures. So we actually need to convert this answer to only have 2 significant figures. So we'll round down to 1,400 amps. And that is our final answer for part A. Moving on to part B, it asks, what are the magnitude and direction of the force? Now remember the right-hand rule. The force is always coming out of your palm. So if we were to look at the diagram given, in the blue arrows, you see I'm tracing the way the current's flowing. Once it hits that wire, it's going down into the wire because the problem asks for the force on the wire, not the circuit. So the B field is your fingertips pointed at your computer screen. Orient your hand so that your thumb is also pointing down, and you will see that the force, your palm, is pointing outwards towards your right. Therefore, we know that the force is going to the right. And to find the magnitude of force, we use Lorentz law, which states that force is equal to current times length of the wire times magnitude of B field times the angle between B field and the wire, which in this case, if we look at the B field, it's going directly back into the page. The wire is sliding side to side, therefore they intersect perpendicularly, as mentioned before, so they have a sine of 90. So we solved for the current in part A, 1,400. Let's just go ahead and plug this into our equation. So we got the current of 1,400 times the length was given in the problem, 15 centimeters. We convert that to meters, we get 0.15 meters. The B field's magnitude is given in the picture, 0.80 teslas. And the angle, as mentioned, was sine of 90. When we multiply all this out, we get a force of 169 newtons. But remember, we have to convert to correct amount of significant figures. So we will round up to get a force of 170 newtons. This is our answer for part B. Now for part C, it's asking, what will the wire's speed be after it has slid a distance of 6 centimeters? So we know that delta x is 0.06 meters. And if you remember your formulas from Physics 1, we know that acceleration is equal to force over mass. We just solved for force, so we will plug our values in. We are given the mass in the problem. Says it's 5 grams, but we want it in kilograms, so we'll multiply times 10 to the negative 3. So we will do 170 over 5 times 10 to the negative 3. We get an acceleration of 3,400. Now, if you pull another equation from Physics 1, we get one of our 3 friends, VF final minus VI squared equals 2a delta x. We know that initial speed is 0. We're trying to solve for the final velocity. We get that the final velocity is equal to the square root of 2 times 3,400 meters per second squared. Don't forget our units. 0.06 meters. Now if we multiply all of this out, take the square root of things, we get a final value of 63.8 meters per second. However, remember your significant figures. We need to convert that to 64, or round it to 64 meters per second. That's our final answer for part C. So just to clear things up, write out our answers. There's no confusion. Part A, we got 1400 amps. Part B, we got 170 newtons. And part C, we got 64 meters per second. Those are our final answers.